Good evening. Welcome to the November meeting of the Baton Rouge Astronomical Society. Tonight, our guest speaker is Walt Cooney, former member of ours, who's now living in Houston. And while he was here, using the 20-inch telescope we have upstairs here at the observatory, he's credited with more than 55 asteroids being discovered. So Walt's going to be talking, I believe, about cataclysmic variables stars. So I want to turn it over to Walt. Walt?
Okay, thanks, John. Hi, everybody.
Hi.
Okay, this is going to go really well. Great audience participation. Okay, so let's see if we can have just a little bit more technical difficulty, though. I will try to share my presentation. Okay, can anybody see anything?
No.
Oh, so sorry.
Oh wait, it almost worked.
Let's see. Oh, okay. I see the share buttons down here. I can raise my hand.
You can try.
Okay, start screen sharing.
Or no. Someone used to Zoom.
Not yet.
Yeah, hang on. Let's see. Oh, shoot. Okay.
Here it is. That looks like your desktop now.
I think that might be.
Now do you see the presentation?
You see your desktop.
Now do you see the presentation?
No, that's not.
Okay.
Alt tab.
We're getting there. We're getting there.
Motherboard.
Take over. You got AMD processor.
How's that?
Nope, not yet.
Oh, shoot on this 5. Is it a PowerPoint?
Yes, it is.
You guys at the bottom, you see the PowerPoint?
Yeah,
PowerPoint?
it's not that.
Okay.
He's used to Zoom. No, he's not used to Jitsi, which is what we use.
Oh, that's why it's not working.
Yes.
Dude, why we couldn't do it as
Basically, why we recommended logging in 30 minutes before the presentation and knock out any of these technical.
Yes.
You're back. You're back.
We can see you now.
It's still fuzzy.
Not the PowerPoint, huh?
How about that?
Yes, we can see it now.
Okay, I take that as a no.
Yes.
Okay. All right. Well, so what is it? 8 o'clock yet? Are we done? Okay. Well, thanks for your patience, everybody. Let's see if we can't go the rest of the way with everything working right. And so here's a presentation. Like John was saying, I used to do a lot of asteroid work when I was at Highland Road Park Observatory, part of Baton Rouge Astronomical Society. But the asteroid work now, a lot of that asteroid discovery work has just been completely dominated by the professional stuff that was built up over time, which is terrific. We were filling a hole as amateurs, filling a gap that where the help was needed, and when that gap was filled by far superior systems, then rather than keep doing something that was then redundant, I moved into different kinds of work. And nowadays, that means a lot of variable star work, and specifically cataclysmic variables. And so let me tell you a little bit about those. You've heard of the kinds of them, maybe without knowing that that's the general category that's used. They're supernovae, novae, and all kinds of other exploding stars. Okay, so as I'm sure you guys have heard, the ancients saw cataclysmic variables, specifically supernovae, many years ago throughout history. As a matter of fact, what we think is the first recorded version or the first recorded occasion of seeing a supernova now is documented on a rock carving in Kashmir, India, that's dated between 4100 and 2100 BC. And the belief now is that that's an illustration of supernova HB9 in 3600 BC. And so can you guys see my mouse moving?
No.
Oh, shoot.
All we see is your title page.
Okay. You just still see the title page still?
Yes.
You don't see the history?
Nope.
Showing it in editing format.
Yeah, it's an editing, not present.
How's
There we go, history. Got
We'll
it.
cut the lights off now.
Okay, boy, that's very strange. But yeah, so now you see my mouse move too, I hope?
Yes.
Yes.
Okay, awesome. So let me blow it up a little bit, though, and see if, let's see.
Well, if you start the presentation.
Well, I was on presentation and it didn't like that.
No.
We can try it again. Can you see it
Yeah.
in presentation mode?
No. It's still in
It's got a weird thing in presentation mode where they'll give you two separate windows, and one of them is a presentation and one of them is just not.
Okay, we'll just go back to this. This is working.
Yeah.
So, okay, so here's that rock I was talking about. And so here is their ancient depiction of Orion, the hunter. And then this appears to be Taurus. For us, it's a bull, and for them, it looks like it's something else. Then they've got this hunter over here appears to be part of what we would call Cetus. And this animal up here is what we think of as Andromeda and part of Pegasus. And this is the sun, we believe. And for a long time, they thought this stone carving was then showing the moon. But it would be kind of strange for this bright object to be that close to the sun. It just didn't really quite make sense. And so what we now believe this to be is that supernova, which happened in Taurus. And so they recorded the supernova, the sun, and the night sky. And the supernova was visible during the daytime like they often are. So anyhow, other times than they've been recorded in history, the Crab Nebula was recorded in Chinese documents. Here's an example of one. And the yellow highlighted script here is the recording of the supernova. And I'm sorry, I can't read it to you verbatim, but there it is. And then Kepler's supernova in 1604 was in the constellation Ophiuchus. And in this book, De Stella Nova, from 1606, you see the constellation Ophiuchus. Then there's this little thing down here that's a bright star with a capital N next to it. And so that was Kepler's supernova, and it's in the right position too. Okay, so let's do a little bit of eye candy here. These are some of the supernova remnants that are so beautiful, show what's left after supernovas. This is one that happened in Centaurus back in 185 AD. And it's actually an infrared picture made by Spitzer and the Weiss space telescopes, 8,000 light years away, 85 light years across, and it's believed it got to be about magnitude -8, which means it was visible in the daytime. You can see Venus in the daytime if you look real hard and you get next to a roof and that kind of thing so that you are partly sheltered. And Venus at its brightest is about 4.7, -4.7. And so, yes, this is visible in the daytime. And then here's a supernova in Lupus. This is the remnant. And this is actually a combination of radio, X-ray, and visible light images to show us this multispectral neat view. 7,000 light years away. It's now 60 light years across. And of course, in 1006, it was 0.00001 light years across. So it has expanded since then. It got up to about magnitude -7, and so was also visible in the daytime. And then we talked about the Crab Nebula in Taurus, supernova 1054, seen by the Chinese, seen by a lot of others. 6,500 light years away. It's only 11 light years across at the moment. And it got to -6, so visible in the daytime. And this was a Hubble shot. And then we had kind of a run on supernovae. In 1572, we had one in Cassiopeia called Tycho's supernova. And this is a neat graphic here from the Hubble Space Telescope Institute, where they have shown the Chandra X-ray picture of the remnant. And you might think, well, so this is what's left of the star that exploded. But actually, that never made sense when you looked at the spectra of that star and everything else. It clearly was not the remnant ash of a supernova. And so this box is now zoomed in this Hubble Space Telescope picture. And we actually believe this star, it was the companion star to the supernova star. And so over in the main box, it's right here, if you can kind of see that. And so what's interesting about it is it's off center. And you just assume that the remnant of the supernova will be in the center and the gas expands away from it. But in this case, this was a double star. And this is the second star that was left on its lonesome after the supernova, and it has traveled some distance away from the center in the last 500 years, give or take. And so I said there was a run on supernova. So we had one 1572, and then just a few years later, 1604, we had Kepler supernova and Ophiuchus. And here's some pictures of that in various wavelengths. So X-ray from Chandra, then Hubble Space Telescope, not so much to see, unfortunately, invisible, just a little bit of the remnant there. And these are all on the same scale. And then this is infrared. So there's much more to see in infrared again. And then these images below zoom in on that same bright arc that's part of the remnant. And so this one only, quote unquote, only got up to magnitude -2.5. Jupiter actually gets a little bit brighter than that at its brightest. And so this one was not ever visible in the daytime. And we don't always only have supernovas in our galaxy. As a matter of fact, the Pinwheel Galaxy has been kind enough to give us 2 in the last 12 years. And so I don't know if any of you remember or had a chance to take a look at this one back in 2011. And it was right here in the Pinwheel. And then just in the last year, that one's gone, but we got this one. And so what's also kind of cool about these two supernovae, only 12 years apart, is they're different kinds of supernovae. And we'll talk about in a second. But this is a type 1a supernova, and this is a type 2. And so a type 1a is a binary star where the white dwarf gets blown to smithereens, and then the companion star goes off. What's left of the companion star goes off in the direction it was traveling, while this supernova in 2023 was actually a core collapse type 2 supernova. And so it was a very, very massive single star that lived its life and finally gravity got the best of it, and it started to implode and then turned around and exploded back out. So two different kinds of supernovae, 12 years apart in the same galaxy. Okay, so we talked about supernovae. There's lots of other kinds of interesting things in the cataclysmic variable star world. Sometimes I think of these stars as stars that go boom. And so there's supernovae, regular novae or classical novae, sometimes they're called. There are also dwarf novae, recurrent novae, nova-like variable stars, polars, intermediate polars, Z-cams, and the list goes on. And so these are all different kinds of exploding stars that are doing different things. And a few words about what they are. And so you've probably read a little bit or seen a little bit about how individual stars are born from gas clouds and then slowly live their life and die. But the cataclysmic variables are almost all binary systems. And so they potentially live a different life, a different birth and death than lone stars. Now, for most binary stars, they're widely separated and they go about their lives like the other one's not even there. No big deal. But if the stars are, quote, close, then things change a lot. And that's when you get these exploding stars. So a little bit of the science behind it first to give you a view of that. This diagram here shows a binary star system, and the two stars are quite close. And this hourglass shape that surrounds them is called the Roche surface, and it's effectively the gravitational boundary for material in this system. So any material that is inside this Roche lobe effectively is gravitationally connected, gravitationally bound to this star. And material that's inside this Roche lobe is gravitationally connected and bound to this star. And this point here is called the L1 inner Lagrange point. And it's a place where the gravity between these two stars is balanced. And so material can go from one to the other across that boundary freely. And that's what's going to happen in cataclysmic variables, mass transfer right across that inner Lagrange point. And so what ends up happening is you have what they call a donor star. It's a regular main sequence star, sometimes more of a dwarf, but still not a strange star necessarily. And then we'll have a white dwarf is the companion, and this regular-ish star, as it grows old, it bloats to the point where it's not only a teardrop, assuming the shape of that Roche lobe, but material starts leaking over from this Roche lobe into the ownership of the white dwarf. And it can't just go right down into the white dwarf because these systems are spinning. There's a lot of motion and, inertia, angular momentum. These things are, angular momentum is conserved. And so when the matter comes off of the donor star, it really ends up spinning down into an accretion disk that then slowly spins down, funnels down into the white dwarf. And at this point here, where the mass that's funneling down first kind of starts spinning into the accretion disk, is called the hot spot, or sometimes the bright spot. And to give you a feel for the size here, this is something like Earth-Moon distance, so 250,000 miles versus, Earth to the sun is 93 billion miles. So these are very small systems and much smaller than what you would normally think of as a binary star that you could see through a telescope as two separate stars. And the orbital period of these two stars around each other is in the range of 1 to 10 hours. And so they're screaming. The Earth Moon orbital period is a month. And so these are going 30 plus times faster in that orbit. And so here's an artist's conception of this, just to give you another look. This is that hot spot where material is funneling down into the white dwarf at the center of this accretion disk. Let's see here. So this is, oh shoot, that didn't work. I'm going to try to talk through this real quickly because it's pretty interesting. I think this is life and death of a binary star where they're close, and it's eventually going to become a Type 1a supernova. And so you start off with two stars fairly close together, spinning around each other, and the more massive star ages more quickly, and just like our sun does, as a star ages, eventually it starts cooling and expanding and moving towards a red giant phase. And so the larger star does that more quickly, and when that happens, it starts spilling matter over into its companion star. But this isn't the same matter spilling we were just talking about, and I'll kind of give you an overview of this as we go. This is kind of why I think it's so interesting. What happens next is the star that's going into kind of a red giant phase ends up enveloping both stars, and they call that a common envelope phase. And the two stars slowly spiral closer and closer together. And then at some point, they eject that envelope of material. And so the whole system now has a lot less mass because they've ejected this common envelope. And you're back to having two stars. But now the star that had been the normal star that grew older faster, now it's a white dwarf. And so now things change again, because now what was the younger star now goes through its aging process. It starts filling its Roche lobe, and material starts coming over and forms an accretion disk, and eventually so much material comes over that the white dwarf reaches the critical mass, the Chandrasekhar limit, and we have a supernova explosion, and the white dwarf is blown to smithereens, and the companion star, which was spinning quickly around this one, that rotational energy is still there, orbital energy, and so it slings off in whatever direction it was heading, and so that's how that other star that remained in that graphic that we saw, the Hubble Space Telescope picture, was way off center. It was this star that flew away because it no longer had a companion to orbit. And so what's interesting about this picture, to again try to make some sense of it, give you an overview, is that the first mass transfer, there were two stages of mass transfer. One where what was the larger star grows older and gives its mass over to the smaller star. The larger star becomes the white dwarf, and now the smaller star ages and it sends its mass over towards the white dwarf. So effectively, you've got the mass transfer going in one direction early in the life of this binary system, and then later in the life that mass transfer has reversed and is going the other direction. And I just think that's kind of cool that it ends up going both ways in this. A little bit more about supernovae. These type 1a supernovae, how bright are they? Well, they rise in brightness 15 to 20 magnitudes, which is just unbelievably bright. And we think now there are two ways to become a type 1a supernova. And so I have to admit, I was kind of cheating a little bit when I was talking about the Chandrasekhar limit a minute ago. It's actually more complicated, and we don't fully understand how all this happens. But we talked about how as the white dwarf gains mass from the donor star, it would pass 1.4 solar masses, the Chandrasekhar limit, and that's when the to get into the fancy physics here, the electron degeneracy pressure of the that keeps the white dwarf from further collapsing. At that point, the mass of the white dwarf is so great that it overcomes that. There's a reaction, and then that star is completely destroyed. What we'll talk about in a second, though, is we really don't quite understand how it ever gets to 1.4 solar masses, because some of these other things happen, like dwarf novae on the way to 1.4 solar masses. So instead of growing, it seems like what happens is they lose mass as they get older. And so it's quite a confusion, a lot of work going on to understand that. What we now believe, though, is about 80% of type 1a supernovae aren't formed by a white dwarf that grows to 1.4 solar masses, but instead it's two white dwarfs that merge, and all of a sudden they find themselves now greater than 1.4 solar masses, and so the same thing happens, they explode. But that just raises another question. The amazing thing about type 1a supernovas is, there are standard candles to figure out how far things are in the universe. And the reason we've always believed they're a standard candle is because when a white dwarf gets to the magic Chandrasekhar limit, it explodes, and so you've always got the same amount of material and the same thing going on, and it's like lighting the same kind of firecracker every time. It's going to give you the same explosion every time. But if 80% of them are really formed because it's two white dwarfs, let's say a white dwarf that's 1 solar mass and a white dwarf that's 1.2 solar masses, and they combine, they merge, and then explode, well, that's 2.2 solar masses. It's not the standard firecracker anymore. And so how does that work? And all I can say to you is that is a good question. And that's what astronomers are puzzled by too. They have theories, but they don't have an explanation. Okay, so going on, I did mention that there's other kinds of cataclysmic variables, specifically supernovae. For instance, the type 2 is the core collapse, where it's just a single massive star that grows old quickly, burns up its fuel, undergoes core collapse, and then bounces out in a massive explosion. So it implodes and then explodes. And the supernova in the Large Magellanic Cloud back in 1987 was a recent example of a Type 2 supernova, as was the second one I showed you in the Pinwheel Galaxy a few slides ago. Okay, other kinds of cataclysmic variables will kind of move down the energy scale a little bit here. There's novae, often called classical novae. And we said, supernovae go 15 to 20 magnitudes brighter. Well, a nova only goes 7 to 15 magnitudes brighter. And in this case, the mechanism is different. So the hydrogen that is swirling down from the donor star along the accretion disk down onto the white dwarf builds a hydrogen layer on the white dwarf. And at some point, the density and the temperature of that hydrogen layer gets high enough that it goes nuclear, and then it is ejected out, and that's a nova explosion. So the entire white dwarf hasn't exploded. It's just this hydrogen layer that has built around the white dwarf. And so both the white dwarf and the companion star remain behind. But this is what I was talking about. The white dwarf actually loses mass. And so, yes, it's the hydrogen layer that explodes, and that hydrogen is blown away. But in the process, that stirs up the underlying white dwarf too, and some of its mass is also blown away. And so that's the conundrum, is how do they keep building mass so that they could reach the magic Chandrasekhar limit when the matter can collect and then blow off as a nova, and the Type 1 or the white dwarf gets smaller rather than larger? And again, that's the famous good question. Some of you guys may remember Nova Cygni, 1975. That's a recent one that was in our galaxy, and you can see that through the telescope now. It's quite an interesting cataclysmic variable to watch, and it's one of the ones that I work, as a matter of fact. Okay, more kinds of cataclysmic variables. There's a lot of different kinds in this zoo, and don't worry, I don't intend to go through all of them. But I'll touch on a few more. So recurrent novae, these are novae that actually do the nova thing more than once. And right now there are only 10 of them that we know of in our galaxy, but we think that's almost certainly because we've only been watching for a short time. And so this is a list of the 10 recurrent novae in our galaxy. And some of you remember, it wasn't long ago that RS Ophiuchi went nova, 2021, and that made news. A lot of people made sure to check that one out. And the big one that everybody's waiting for right now is T Corbor, T Corona Borealis, and it's set to go off, we think, sometime around this spring, after the last eruption in 1946. So the astronomers, the pros, are very excited about this. They have telescopes primed and ready all over the world, and it will probably be an amateur astronomer somewhere who sees T Corbor go off, and lets everybody know through channels. And then the pros are all going to get their scopes in that direction as quickly as possible. And as a matter of fact, a little point of interest, some of you, I'm sure, remember Dr. Brad Schaefer at LSU. So it's his prediction that this will go off sometime this spring, plus or minus 3 or 4 months. And he gave a really great AAVSO talk on it a couple or 3 months ago. You can go out on the AAVSO HQ YouTube channel, which is just searchable. Anybody can go look at it. And he gave a presentation on T Corbor and recurrent novae in general. It was really fascinating, and so it might be worth a minute of your time.
It was a great one. I watched it, Walt. It was a great presentation by him.
Yeah, is that John?
Yeah.
Yeah, no, I remember seeing you on the presentation. Yeah, it really was great. He did a terrific job, and I think there are many hundreds of views of that YouTube video already of people who couldn't watch it live. And this will also, it'll go all the way up to about second magnitude. And so it'll be a bright star where there was no star to be seen before, and so it will get a good bit of news coverage, I expect, as well. So coming to a sky near you. Okay, we talked about novae, recurrent novae. Well, so the next step down the energy scale is what's called a dwarf nova. And these rise in brightness only something like 2 to 6 magnitudes. And they have a different mechanism as well. For these, the hydrogen in the accretion disk doesn't. It's not that it builds a layer on the white dwarf, which then explodes. It's actually the hydrogen in the accretion disk itself that will, in some areas, get the density and temperature required to go nuclear. And so that's not as energetic. There's not as much material involved as if it were the hydrogen layer that's forming down at the white dwarf itself. And there's all kinds of fascinating variations on these dwarf novae. An outburst is when the accretion disk hydrogen ignites. But what's called a super outburst is when it goes even brighter than normal in addition to a normal outburst. And that's when you get the accretion disk hydrogen lighting off, but you also get hydrogen lighting off right where the matter is falling into the white dwarf. So you get the double explosion, twice the hit there. Other things, interesting things going on. There's something called a super hump. And these are, we believe these are warpings of that accretion disk that cause periodic waves that can be seen in a light curve. And then there's something really cool too that I would love to see in person someday if I ever happen to have the chance to go by a cataclysmic variable in person. And that's called flickering. It's like the twinkling that we see at night on stars, especially down towards the horizon, but it's not an effect of our atmosphere. It's actually fast nuclear changes at the cataclysmic variable itself. They used to think that this was entirely at the hot spot, where that matter from the donor star is contacting and becoming a part of the accretion disk. But we have since realized that that's actually not the case. Most of the flickering is down where the matter is falling into the white dwarf. And so I kind of think of this almost as like a sizzling, or like you'd see a fuse on, the fuse in the movie, the old movies. It's the fuses go into the dynamite or whatever. It's that flickering, and so that would be pretty amazing thing to see on a stellar scale. And you can see it in your data if you're doing photometry of these. It looks like you just have noisy data, bad photometry, but in reality, it's real. It's just sitting there flickering. So here's a couple example light curves. These are from the AAVSO website, and these are contributions of amateurs like us. And so SS Cygni is a famous dwarf nebula. It runs between about 8th magnitude and about 12.5. And its period is on the order of weeks. And so you get lots of these sinusoidal is even a fair way to say it, but these outbursts and then fall back, outburst and fall back. And to explain the graph a little bit more, the black circles are visual magnitude estimates by people with either binoculars or a small telescope. And the green circles are photometry by somebody with a CCD. And what's so cool about this is look how well those agree. And the important thing that comes out of that for me is that the stuff that people are doing, the visual astronomers who are doing visual magnitudes of variable stars, that's really good work and really helpful. And even with all our fancy equipment and everything else, it most definitely has not put the visual observer out of business. And we still really need them, especially because, for many of these stars, we've got more than 100 years of data. And those super long time frames like that, at least according to us humans, is a tremendously helpful thing as we try to figure out what's going on. Real quick, the other one I'm showing you down here, SU Ursa Majoris, that's one that has these super outbursts. And so these smaller jumps that you see are the regular outburst, which is a brightening of the accretion disk. And then sometimes you get this extra bump where it's more than a magnitude brighter. Here's another one over here, 1.5 magnitudes brighter or so. And so that's when the area where the hydrogen is falling down into the white dwarf also goes bright. And anyhow, so that's what a super outburst looks like in a light curve. Okay, these are cool. This is a Z-cam. It's called that because the first one ever discovered was Z camelopardalis. And so it bears all of them that are like that bear that name. And so Z-cam has these regular outbursts that happen frequently. You see it going up and down here. But then every so often, on its way back down, it gets stuck. And it just sits there kind of humming along, in this case at about 11.5. And after some indeterminate amount of time, it finishes its going down and starts cycling again. And then for some unknown amount of time, it gets stuck again. And so we're, of course, trying to figure out what the heck's going on here. This is recent AAVSO data that I pulled. And so right now it is in oscillation phase. And it might do that for another 2 days, or it might do that for another 3 months. And then it'll get stuck again. And so continuing to watch these, continuing to get data is how we'll eventually figure out what in the heck is going on with these. These are kind of cool. This is what's called a nova-like variable. So it's a cataclysmic variable that doesn't have cataclysms. It doesn't explode. Which, of course, that doesn't make any sense, right? Well, when you look at these with a spectrograph, you'll see the spectrum looks just like the spectrum of a nova. But they're just sitting there at fairly constant magnitude, like in this light curve here. A little bit oscillation, but fairly constant. This is only 12.8 to 12.9, so 1/10 of a magnitude variation. And so what they think what's going on here is that these are cataclysmic variable stars that are basically always in cataclysm. They have real high mass transfer rates from the donor star down to the white dwarf, and so they're always on fire. They're always lighted off. And what's interesting about this one that I picked out, because I think this is pretty neat, is that this is one that's eclipsing. And so this deep dive from 12.9 to 13.7 is when the white dwarf and the accretion disk both are eclipsed behind the donor star, which is the larger of those things. So now we know how bright the donor star is. It's about 13.7 by itself, because at this point, white dwarf and the accretion disk are both hidden behind it. So, and I just think that's a really beautiful light curve, or you can show the light dropping and coming back up and then going back into oscillation. Another favorite, these are called polars. And so our Earth, our sun, have modest magnetic fields. Earth is about half a Gauss. Sun is about 1 Gauss. But a polar has a white dwarf with a magnetic field between 10 and 80 million Gauss. And so just unbelievably strong magnetic field around the white dwarf. And it is so powerful. If you look over here in the graphic, the material that's falling down, being pulled over from the donor star to the white dwarf, it never forms an accretion disk because that super powerful magnetic field grabs it at some point and then pulls it up and back down into the magnetic poles of the white dwarf. And so it's a cataclysmic variable that doesn't have an accretion disk because of that.
Could that eventually form a magnetar?
Yeah, that's a good question, and I don't know.
Magnetars are usually neutron stars. True, but I'm just asking because the high magnetic field.
It is, and I really just don't know enough about them to know what they're, how they formed. I think the answer is no, but that's just from vaguely reading about them not that long ago, and I didn't really commit it to memory. But here's an even cooler one. So these are what's called intermediate polars. And so this is one with a strong magnetic field in the white dwarf, 1 to 10 million Gauss instead of 10 to 80. And so in this case, the super strong magnetic field allows the accretion disk to form. But then as the material spirals down from the accretion disk, eventually it's close enough that the somewhat weaker magnetic field then grabs it out of the accretion disk and pulls it up and back down into the magnetic poles of the white dwarf. And so now we've got an accretion disk that looks like a donut. And so these are just really cool. And I do work on these, photometry on these all the time. And here's the most famous of them. This is the one that they're all named after, DQ Her. And it also happens to be one where it's a line of sight variable to us. And so it has these beautiful eclipses. Now, I don't have them exploded so that you can see the nice dip and rise, but you just see all these eclipses that happen on this star. And so people are looking at things like period changes, the speed of the white dwarf, the orbital speed, all those kinds of things to understand how these systems work and how they evolve. So that's the partial look at the zoo of cataclysmic variables. And where are we going with all this? Well, still a lot to understand. Amateur astronomers are contributing a lot to this. We're trying to figure out how in the world you really do get type 1a supernova in the first place, and how do you get there from here? How do you start with a cataclysmic variable and then end up with a white dwarf that's above the or at the Chandrasekhar limit and explodes? One really fascinating thing that's been discussed for years, and now they've got some pretty good evidence that this is what's really happening, is dwarf novae-like variables. They're all a spectrum of time. They're snapshots in time, and that many of these cataclysmic variables go through many of these stages. So the dwarf nova today might be a recurrent nova later, might be a type 1a supernova later, for instance. And actually, we've got some recent examples, just a few, where a star that had been a dwarf nova has gone nova. And so clearly there's a timeline there in evolution. Next big question, we mentioned this, are all novae really recurrent? Do they all go off every so often? But we've just been looking for this short period of time that we've been looking at stars, and so we just haven't been looking long enough to know. And I think most people feel like that many or most, if not all, novae really are recurrent, but still active effort there. I won't go into these last little bits, but there's all kinds of other things. There's what's called negative super humps. There's period bouncing and period gaps. We're trying to understand flickering better, and many, many, many other things. And the reason why we care, other than the fact it's just really neat, is that cataclysmic variables like this are really good ways to understand the physics of accretion disks. And accretion disks are important in lots of things like black hole formation and planetary system formation. The great thing about cataclysmic variables is they do so much of this stuff that they do on very short time scales. And so we can learn a lot about how these things work, the warping of accretion disks and all of that kind of thing, by watching these fast systems, and then use that to understand better slower systems, like how do you form a planet in a protoplanetary system. Okay, just a couple more slides just to mention ways that if this is interesting to you, you can participate, you can catch the same sickness that I've had for a while. And so the AAVSO, American Association of Variable Star Observers, all those light curves I showed you were from AAVSO data. All that's freely available on their website. You are welcome. Just go fiddle around and see what your favorite stars do and are doing now. As a matter of fact, both visual and CCD/CMOS work is really important. The great thing that's doing for us is we get multi-year or multi-decade light curves, and the pros just can't do that. They're very excited if they can get a week on a big telescope, and if they get the Hubble telescope, they get it for an hour. And so there's so much that happens in astronomy that's on long-term time scales. Of course, it'd be really nice if we could look over millions of years, but we're pretty happy at least we can do multi-years and multi-decades right now. Another thing the AVSO folks are, as I mentioned, we're the sentinels for these recurrent novae. We're going to be the folks who yell, "It's going off, it's going off." And all the pros will then jump on it with their 400-inch telescopes up on top of a mountain somewhere and try to catch it as early as they can. And then this last one is one that I have also participated in too, which is really pretty neat. Effectively, we are ground support for the Hubble Space Telescope. And so there's a lot of active research in cataclysmic variables. As a matter of fact, anecdotally, what they'll tell you is there have been more PhD dissertations written on cataclysmic variables than anything else in all of astronomy. And because they do so many things, there's so much to learn there. And so a number of pros are used in the Hubble Space Telescope to investigate cataclysmic variables. And the particular instrument on the Hubble Space Telescope that they almost always use is the Cosmic Origins Spectrograph. And that's because it's an ultraviolet spectrograph. And a lot of the interesting things that they want to see in cataclysmic variables are happening in the ultraviolet. And that's really fantastic, but there's a problem, and that is that the Hubble Space Telescope has one instrument that could be damaged by overexposure, and it's that one. And so generally, the professionals want to examine cataclysmic variables when they're not in outburst. They want to see what they're doing in quiescence, as it's called. And so normally that might be, 16th magnitude in quiescence, but in outburst, maybe it's 12th magnitude or something like that. And that would be bright enough to damage the instrument on Hubble. And so they're taking a risk doing this. And the way that they help mitigate this risk is they work with the AAVSO, to identify all the cataclysmic variables that Hubble is going to be working and when they're on the schedule. And they put out the plea to amateurs to follow those stars. And for at least a few weeks before one comes up as a target, amateurs start working it. And if it goes outburst in those few weeks, well, they go ahead and call it. And of course, they don't use Hubble on it. And there have been several of those where we have seen it go off within a week or two of Hubble moving to that target. And so they have called off the observation and rescheduled it. But even at that, the Hubble Space Telescope group requires at least one or more observations of the cataclysmic variable from the ground within 24 hours of actually allowing Hubble to look at it. And so time is of the essence. And it's kind of neat the way they do that too. They in the Hubble schedule, where they would have the cataclysmic variable in the menu of execution, they put just blank sky in there, and then once they get confirmation within 24 hours of when they're supposed to observe it, that's when they actually upload the target information into Hubble, so that it's basically a fail-safe. So they don't even really load the target coordinates into Hubble until they've gotten that 24-hour clearance. So anyhow, and so one of those is going on right now. I've forgotten which star it is, but Hubble is going to be looking at it on November 17th. And so amateurs are watching it and reporting brightness as we speak. That's all on the AVSO website too, if you want to take a look. And then one other amateur astronomy effort is what's called the Center for Backyard Astrophysics. And it's Professor Dr. Joe Patterson out of Columbia in New York, who back in the early 90s decided to take advantage of the fact that amateurs love doing this stuff. And we could supply him with fantastic data that was far and above what you could ever get on a mountaintop with limited time to go around. And so for all these years, he's been putting together observing campaigns, and the members of the CBA have worked those stars for him. He's done lots of really great work. A lot of papers have come out of that, and it's really been an amazing effort. Quite the success story in a professional amateur collaboration. And with that, I'll end and open up for questions if anybody has any.
Walt?
Yeah.
Original question, are you ready for vice president yet?
What's that? Sorry?
We have nominations tonight. Do you want to run for vice president?
Hello? I think
That's a good
Hey,
one.
you're just like most of the members, can't hear a thing.
Yeah. Okay, there you guys are. I've taken my screen down. I don't know what you guys are looking at now.
Well, what he's asking about there, normally in our nomination ones and our election, if you get them, go away from where we're doing it, when you come back, you're gonna be an officer.
Wait, what's that, John? I can almost hear you, but
Hey, Walt, my wife says this is selective hearing.
now that I heard. So,
Good question for you.
yeah.
I read a few years ago that if a white dwarf has a very, very high spin rate, it can affect
the brightness of the supernova because the high spin rate actually.
Could you get closer? I'm sorry, I really actually can't quite hear.
Where is the microphone?
Over here.
It's right over here.
Great.
Can you hear me now?
Yes, yes.
Yeah, I read an article a few years ago that was talking about white dwarfs with very high spin rates, that if they were accreting matter, they could actually go significantly over the Chandrasekhar limit before they pop. This was about maybe 7 or 8 years ago. Could that possibly influence?
I'm not sure I heard you completely, but you were talking about that the white dwarf accretion rate can be fast enough to go past
if
the.
the white dwarf was spinning very, very fast, that spin would resist the gravitational collapse somewhat and allow it to accrete more mass than the limit before it blew up.
Yeah, I don't know. I haven't heard that, but I admit to you, there's.
8 years ago, I forget where. I don't know if it's in Scientific American or what, but it's about 7 or 8 years ago.
That makes some sense.
Yeah.
Well, honestly, it makes a lot of sense. And really, it is kind of difficult as an amateur astronomer to have any hope of keeping up with all of this. It has been the nice thing about working with some of the pros to have people who really know the answer to those questions to ask them. As a matter of fact, if anybody is interested, I'm also the co-lead of the Cataclysmic Variables Observer section for the AAVSO, and we are having a Zoom meeting on December the 3rd, Sunday, December the 3rd, 1 p.m. our local time. And our special guest is going to be a cataclysmic variable astronomer, Dr. John Thorntonson, out of Dartmouth. And he's going to talk a little bit about T-core Bohr, which everybody's interested in, but it's also going to be a chance to ask somebody who can really answer those questions. So anyhow.
Can we get a link to that meeting?
What you can do is if you go to the AAVSO website and oh gosh, I wonder if there's anywhere I can show you how to do this. I'm a little afraid to try. You know how that goes.
There's a chat window to the bottom, the thing that looks like a little talking bubble.
Okay.
Like you see the microphone, the camera, the screen, and then there's
I see that.
That'll bring up a thing on the left.
Okay, I can post a link, although it'll take me just a second to get to it. I don't suppose you guys can see my screen right now.
You could share the screen, and that'd probably also do it a little bit easier.
Well, let's do that because I'd like to show you how to get to it rather than just post a link that kind of gets lost forever. Hang on just a second.
Real bean Scott over there.
Well. Okay, so you should see the AAVSO webpage right now.
Yep.
Fantastic. Okay, so this is the homepage. It's just aavso.org. And you can go to this partway down as something called Observing Sections. And here are cataclysmic variables. There's our little white dwarf and its accretion disk and all that. And so this is, I'll show you one other thing while we're here. This is a thing that Dr. Schaefer wrote up for us on what amateurs can do science-wise to help astronomers with recurrent novae. Here's T-core Bohr, we'll mention that. So here's all kinds of different activities, and he was very nice to do that. But you can also go to the Cataclysmic Variable Forum, and go down. Here's one of the 8 Hubble Space Telescope CV campaigns that I mentioned. This is where those are advertised. And here is October 1st section meeting summary. And then here is the December 3rd meeting, where I talk about Dr. Thorstensen coming from Dartmouth. And you just go down here and you click on that and you give it your name and your email address, and you do not have to be an AAVSO member, I don't believe, and hit register, and it will send you to your email here a link to the Zoom meeting, and then you can join us. So if anybody's interested, I think it'll be great, and especially because it's pros and amateurs. And that just makes for interesting conversation. So, you're welcome.
Well,
Anything?
I have a question for you.
Okay.
I just read a little bit, I think it's just a small article I was reading today, that there's a star out there that is 1/2 of it is hydrogen and 1/2 is helium, almost a full hemisphere worth of hydrogen and 1 of helium. And they just don't quite understand how it's happening. That there's almost like a sharp dividing line between hydrogen and helium.
Yeah, I have a little bit. Is that John?
Yeah.
Okay. Yeah, I have. As a matter of fact, I was just up at the AAVSO conference in Boston this past weekend, and there was some discussion about those. I can't really repeat it. I don't remember it well enough, but like you say, people are scratching their heads. One of the things that's kind of interesting that I had not known until a few years ago is that when we say white dwarf, that's not fully describing them. There are different kinds of white dwarfs. There are helium neon white dwarfs. There are oxygen white dwarfs. I forgot, but depending on what the dominant material is that makes up the white dwarf, they have different compositions. And so you end up getting different physics, different types of cataclysmic variable activity, and different types of novae, for instance. If it is one of the different kinds of white dwarfs. And so it's not unusual that there would be hydrogen and helium, but like you say, there's some evidence that they are there in strange configurations and strange proportions, and it's not understood. That'd be another great question for Dr. Thorstensen, by the way.
Okay. If I can manage to make that, I'll ask him about that one.
Okay.
Well, a
Uh-huh.
serious question about CCD. Would any normal single lens reflex with a charge coupled device on it work?
You mean like?
Out of this house, or just normal picture taking?
Yeah, you're talking about using the DSLR for photometry?
You know, just any. I'm just asking.
Yeah, the answer is yes. I think I'm still sharing, right? I can go back to the AAVSO home. Can you guys see this?
Yeah.
Okay, and so let's look at let's look at SS Cygni again. So you can type the name of the variable here in the Picastar, and you can tell it to plot a light curve. And this is where I got those light curves you were looking at. And I will show you DSLR data. So all these different color symbols are different kinds of data, different filters, B filter, BVRI, that kind of thing. And so I'm going to shut off a lot of them. Actually, I'll shut them all off. Won't let me do it like that. I'll shut off the visible, faint, blue, V, R, I, U. Okay, why is that not working? I guess it's just slow. But so these symbols over here, Craig, TB, TG, and TR.
Yes.
This is RGB DSLR photometry.
Okay.
And you have to read a little bit of detail about how they do that. But yes, okay, so now it's working. Well, just really slowly. Sorry about that. I picked a bad star because there's so much data on this one. Everything works slowly. But maybe it's picking up there. Okay, so this is, let me turn this on. There hasn't been a whole lot of DSLR photometry done on SS Cygni, it turns out. But that's what, these are all data points within the last, 600 days, so 2 years, give or take. This is DSLR photometry done with a small telescope and a DSLR camera. So definitely the answer is yes.
So it doesn't take a lot of money to get started. If you already have that equipment.
Well, it doesn't, and as a matter of fact, the cheapest way to get started is a pair of binoculars and your eyeballs. And yeah, I know. Maybe that's not the best way for some of us. I agree. But there are a lot of variable stars that are 4th, 5th, 6th magnitude, and binoculars and eyeballs are a terrific way to contribute that way.
Can you just send in the raw images, or do you have to do a set amount of processing?
There is some processing, although they try to make that as easy as possible. There are some programs you can use to do that, including if you go to this one called Tools and Observer Resources, and you click on this thing called vPhoto and log in here. And so this is online photometry, a tool provided by the AVSO. And so this is an image of mine, actually, of V838 Monoceros. And it calls up the image for you after you have uploaded it. And now, of course, it does take a little bit of time to figure out how to use all this. But then let's see. Here is, okay. So this is how I would do photometry of this star. This is the variable star right here. This is a comparison star. This is a check star. And so you can see the little inner circle here. On these three, you can barely see it on this one. That's in that inner circle. It's going to count all the pixel values. Basically, it's going to count how many photons hit that area. And then it's going to take an average of how many photons were out hitting here in kind of plain sky. And so it's going to subtract this number from that average to get just star photons, as opposed to sky photons and light pollution photons. And we got way too many of those. And so it will do that math. And then you can come over here and click the photometry report. And so for that image, V838 Mon was running 15.383 magnitude. And then you can click this, and it generates the AAVSO report. And it just generated the AAVSO report. There it is. And now you can save that somewhere on your desktop or wherever. And you go back to the home page here, and you go submit and access data. You tell it you want to upload photometry, and you browse to wherever that file was. This is a different file, but here's one here. And here's this was one where it had lots of data for a particular star. And it lets you look at your data one last time, and then you hit submit, and it's in. Now, I won't hit submit because I've already submitted this data. and so you don't want your data in the same thing twice. But so that's how you can do the whole thing with software available through the AAVISA website.
Well, are these photos just one sub or are they a stacked set?
Yeah, this is actually a stacked set. So the star here is CC Sculptor, Southern Hemisphere star. I was using the telescope in Australia here, and it's a cataclysmic variable. And what you want to see with cataclysmic variables, a lot of them do things on very short time scales. And so rather than just having a single magnitude estimate from one image on one night, you might sit on that star all night long with your telescope if you're a CCD observer. And this wasn't all night long. This was actually just 11 images in this case. And then I moved on to a different star and did that one all night long. But yeah, so this is, I guess it's every 3 minutes is how fast I was taking an image of this one. So 11 frames. So this is probably about 35 minutes or so of data. You can also go see your data once it's submitted. It's submitted instantly. And so let's look at TV. No, let's look at that one, CCSCL. And I'll plot a light curve. And so this is, you can go down here. These are the people who have submitted data. These are their observer names. I'm CWT. And if I click the box there, this was all of my data. So each one of these sets here is a different night where I did some observation of this star. And all these others were done by other observers in other locations. And the nice thing is it looks like we're all getting data that agrees pretty well, even though we're different systems, different locations, different everything. And before you think, oh, wow, 17th magnitude, how in the world? Well, this was done with a 12.5-inch telescope. And now it's a 3-minute exposure to get enough photons to get pretty good data. But you can do 17th magnitude with a 12-inch telescope. So yeah, 6-inch, 8-inch telescope can do a lot. Okay, other questions?
Well, thank you very much, Walt. We appreciate it. I hope to see you over here sometime soon. Yeah.
Well, I appreciate it. Thanks for giving me the chance to talk. It's nice to talk to everybody. I appreciate it, and I'll also say, if you get interested in this and want to learn some more about it, I'm really happy to help out. I'm working with lots of folks who are getting into this now, locally and around the country, it is an illness, but it's not so bad to catch it. So
remember, there's a 20-inch scope up there, probably with everything you need.
it's probably what, Craig? Sorry.
I said there's a 20-inch scope on top of this building with probably everything you need.
For sure. It could do some awesome stuff. It can do every bit of this kind of thing and a lot more. So anyhow, okay, I will step away then. Thanks, everybody.
Todd, are you back there?
Yeah.
Okay. Thank you very much for attending this meeting here, the live presentation of our speaker, and we're now going to stop the live streaming and go to our regular business. Thank you very much.